Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today we're going to talk about switching regulators, a boost converter, and kind of a special type of boost converter. This is what some people might refer to as a polyphase or two-phase converter. So here, let me just kind of show you what we're getting into so we can come over here at the bench and take a closer look. Here's your boost regulator circuit. You got your input capacitor, your output capacitor. Now, the magic starts with the inductor and the transistor and this diode. So, when you first turn on the circuit, transistor's open. So, V in goes right out here to V out. So, let's just say it's 12 volts. You get roughly 12 volts here was the diode drop, okay? Then this transistor turns on, pulls this node, this switching node, down to 0, and then lets go. But when it pulls down to 0, you got this current that circulates this way. It's one of our power loops, okay? Charges up that inductor. When the transistor turns off, the inductor wants to keep on, the current wants to continue to flow through it, right? It doesn't want to change instantly. So it has another direction it can go, another path. It goes to the diode, goes to the capacitor. So it boosts the voltage up from initially what was 12 volts, the same as V in. Now it boosts it up even higher, okay? And then it just keeps on doing that until we regulate the output. Or there's a duty cycle control. We'll talk about how to design these things in another video, but this is just kind of a concept. Really cool thing. If you're doing high current on one of these things, then you're going to get some pretty good switching current, some ripple on your input and output, right? And you're going to have a lot of current going through your inductor. So one of the ways to reduce the size of your components and to smooth out that ripple. So let's just say that this is the waveform. The switching node goes down to 0 and then pops up. Now this voltage right here is after that's been running for a while. We're regulating, let's say 50 volts here. So this is 50 volts. Pulls down to 0, pops up. So there's a lot of dead time. And the duty cycle depends on how much we're boosting, the voltage difference between input and output. We'll talk about how to design those in another video. For this one, I just want to show you the concept of polyphase or two-phase converter. What the idea is these components start getting pretty big. Your inductor gets big, the transistor, you got a lot of switching currents, ripple on your input and output capacitors because, look at all the time it's off, right? So what you do is you fill in this dead time with another switch. Let me show you. Alright, so I drew another regulator right here. Inductor, a switch. I just drew a switch to simplify a FET right here, and then diode. Okay, so this is in parallel to this converter, and it ties in. The two diodes are diode-ORed at the output. Okay, so they share an input capacitor, they share an output capacitor. Otherwise, they're just in parallel. So if the switching node here looks like this, then the switching node here looks like this. So you get pulses in between. So that way, you only have dead time in between these pulses. You get a lot less dead time. So it's almost like you're pulling current almost continuously through Cin. I mean, not quite, because you got some dead time still, right? And then, but it's a lot higher. You've doubled the switching frequency, so the capacitors can shrink in size in comparison to having one regulator at one switching frequency. So, let's say in the case we have here, 150 kilohertz, 150 kilohertz. Now it looks like 300 kilohertz and 300 kilohertz. So that's the beauty of that. The other thing is FET isn't switching at 300K, it's switching at 150, so the switching losses are less. And it's off more often, so you don't have as much conduction losses. So the FET can cool down in between. So, there's some advantages. The inductors can be smaller too. So now, by the way, these diodes, they would be FETs, what we would call synchronous rectification. So you have less losses than diodes, which would really be Schottky diodes if we did use them, but we can get lower losses with a FET. And the kind of control chip we would use would control all four of these FETs with the right timing. And that's what we have here on the board. So let's come over to the bench and take a look at this board And then let's look at some signals, okay? So the kind of signals I'm going to show you are the switching nodes, so you can see the clock cycles, kind of the basics. And then you'll see how that affects the ripple voltage, because you get some interesting looking ripple, okay? It's less ripple, but it's kind of an interesting frequency, because you have all this dead time, and with regulation, things just kind of look a little different. But yeah, let's come over and take a look at that. I think I'll show you the spectrum so you can see what the spectrum looks like. We should see a spike at 150 kilohertz and 300 kilohertz, so we'll take a look at that. And the noise is actually going to be pretty small. It should be smaller than a normal converter at the same power. So yeah, polyphase or two-phase converter, because they're out of phase with each other, right? So, all right, so let's just come over, take a look, and see what we see.
Alright guys, let's take a quick look at the data sheet for this. This is a demo manual here. Let me zoom in. Alright, the demo manual DC2061A. This is for the LTC3784 high efficiency polyphase synchronous boost converter. Yeah, this is it. This is pretty cool. This is what you get with the eval card. Now here's the specs. The input voltage goes from 6 to 60 volts. The output is 48 volts. And it's 3% plus minus 3% tolerant. So that's pretty good. Now these maximum inputs are actually for the chip. For this board, we're going to run 6 to 47 volts because it is boost. So we have to be below the output. And we'll boost to 48, and it's 0 to 3 amps on this board, but I'll show you how you can change that. The output ripple is spec'd at 200 millivolts peak to peak. I think we'll show that it works pretty well. And nominal switching frequency is 150 kilohertz. This is per converter, because up here it shows 2 by 150 volt converters. So let's take a look. Talks about the quick start. Okay, here's the next page, and here's the board. Terminals on the top for the input voltage. They have these measurement terminals on the side. On the output, we have it to the right, and you can see the little terminals. And here is the converter right here, just left of center. It's a really small controlled chip, and across the top here is one converter, and across the bottom is another converter. You can see it's like a mirror image of each other. All these transistors are not populated. You could populate an extra transistor right here and up here, or you could take off this transistor and use a diode so you could see how well Schottky works. So this board's set up to experiment. Over here on the left, see this mode? There's a little jumper. You can select constant current mode, pulse skip, or burst mode. And then there's some measurement points here. You can see all the measurement points around here, all these little gray dots. There's some other jumper that you can select. You can change the phase if you want to. You can turn it on and off. And there's an over voltage protection feature. Okay, so let's scroll down. Now this is good measurement techniques for low output. It gets rid of the long ground strap that picks up high frequency noise. Here's the next sheet. Now this shows a soft start, and here's a parts list. All right, I rotated the schematic, and down here in the border you can see the title of this. Now let me zoom in on the schematic. You can see the output terminals right here on the right in the middle, and up to the top is the input terminals. That's the schematic. I'll zoom in on those just so you can see the capacitors, and there's a bunch of capacitors. Let's scroll over. The input comes in here. You got sense resistor to monitor the current. Okay, now here's an inductor, and what I'm going to do is show you one of the boost converters. So here's an inductor for the VN, and here's the main switching transistor right here, and here's the drive signals right here, and here's the synchronous diode, the Q2, this FET right here. It's kind of drawn strange, but you can see how the connection comes down here to the V out, okay? So yeah, it's kind of drawn backwards, so it makes it a little bit harder to see. And then down here, we have the same thing. Here's a switching transistor right here. It's pulling the current down to ground. So again, it's upside down and backwards. This one's really strange. Here's a synchronous diode, or the synchronous FET. And you can see it's tied to the output. So they're diodored. And here's the input. It monitors its own input current. But you notice there's no caps here. They share the same input capacitors. And then over here, we have the control chip. So all the drives on this right side, the sense for one of the converters up here, the sense for the other converters down here, and then you set the frequency and all that stuff over here on the left side. Okay, here's the pulse and skip and burst mode right here. So you see all the jumpers right there. So yeah, sorry, schematic's kind of drawn the way the board is, so it makes it a little bit difficult to read. Okay, here's some more of the schematic. Some input control signals here on the bottom. This is a little switching regulator to supply a bias voltage for the chip. So this is just a little small converter, pretty cool. Alright guys, so input terminals up here, output terminals here, and they've made it easy so you can just plug these in. And there's also all these test points all over the board, both sides. And then here's the jumpers for constant current and the burst mode. So we'll show you that. Now burst mode and pulse skip, sometimes it's more efficient to use those, and depending on the inductor and your design, sometimes it works better. Often it might not, and so you'll use constant current mode. So yeah, just options there though. You can see where all the transistors are not installed, and here's actually the rectifiers side, and these are the main switches. So here's one for one channel, here's another channel up here, and just a lot of ceramics. And there's only 2 output capacitors installed, and you see no aluminum electrolytic for the input capacitor installed. Really nice, small, compact design. Then you're wondering where the inductors are. Now, there they are, big old behemoths. Now, imagine if you had to get all that current through one inductor, how big they'd be. Okay, now here's some more output caps, and there is one input capacitor right there. So more ceramics, and you can see the sense current resistors right there. There's kind of a close-up of it. And over here in this corner you can see that little converter that's operating by itself, a little small inductor. Let's switch the board back over so you can see, so you can kind of see the close-up of that. And there you go. Pretty nice. You can see the big planes on the board. So big power planes, right? Same on the other side. So you see the output plane right through the center, and you see the input ground plane all the way around the edge. And up here you can see the same thing. Input voltage, the ground all the way around, and the output plane right there, power plane in the middle. Nice usage of copper. Alright, so let me just go over this setup. I've got the board all wired up. I've got the input power coming in here, the output power going to an active load right here, and I'm going to use these. I'm going to start off using these 2 scope probes here. They're from my Pico scope, but they're tied to my MixSig, which I'm going to show you. And I'm going to put one on each of the 2 phases so you can see the switching node and see how they work in relation to each other. Okay. Then after that, what I want to do
is I want to show you the input voltage ripple with this differential probe. And this one is tied to this DP10013, and it's on 50X. Okay, it's a mixed sig. And then this differential probe on the output, we'll look at the output ripple, and it's tied to the DP1007, and it's set at 10X. Alright, so then I also have the Handtech, the CC65, set at, I'm going to put that in the 10X position, and I'll show you the current coming into it so you can kind of see what the current ripple looks like feeding the amplifier. Alright? Alright, so let me show you the power supply. I am going to use this guy right here. So I'll use the Kaiweets power supply right there. I think I'm going to set it to 15 volts. And I'll be able to read the power off to you as I do that. Well, after I put the load on. Well, I think we can look at the quiescent power too. Okay, and then scanning over here, there's the GW insect scope. But there is the active load. Okay, the IT8512A active load. And that is set, actually it's set right now for 2.5 amps. And so when I turn it on, I'll see the voltage up there. So it'll be 48 volts, so it's going to be somewhere around 150 watts. Okay, and then down here, we have our mix sig. Alright, and here is the mix sig. Channel 1, 10X, channel 2, 10X. So 10 volts per division. So we're going to see some square waves as the switching node starts to pump as I turn on the power supply. So let's go ahead and do that. Now, by the way, I have them referenced just slightly different from each other down here at the bottom of the screen, just so it's more obvious. Okay, I'm bringing up the voltage to 15 volts. Alright, I brought up the power, and you can kind of see them switching, and they both go to, they kind of look funny right now, right? But let's just look at the volts. 10, 20, 30, 40, about 48 volts, which is what the output is. So here, let me get a few more cycles so you can kind of see what's going on here. So it's switching, then nothing for a while. You can see that it switches, and you can see little pulses. That's because there's no load. Now once I put on load, then we do that. Now we can zoom back in. And there we go. Okay, I'll just go ahead and freeze that. Alright, power supply just kicked on. It's putting out 130 watts. I'm going to freeze that and turn off the load. And the fans on the power supply turn off. That's nice. So I'm going to go ahead and bring this up to this grid right there. And bring the blue one up to the same grid right on top of the yellow one. Whoops. Okay, there we go. So you can see how there's a space between pulses. Now, one thing is switching at 147 kilohertz. And let me zoom in on that screen. Okay, I zoomed in on the screen. See 147 kilohertz here. I've got the cursors up here, but I could set them up if I wanted to, but kind of wasting time, I guess. Okay, I guess I could use the arrows here. Okay, they're pretty close to the lines. The cycle time is, let's see, 6.76 microseconds. So that's probably going to be somewhere around 147K if I got that close. Now, let me see what the on time is. And the on time is about 2 microseconds. So that's roughly about 30% duty cycle. Here, let's see if we can get a measurement. There we go. 31%. Let's get channel 1 as well. 31. I can get rid of these guys. We don't have those up right now. There we go. So, yeah, we got about 31% duty cycle. So, if it's 50%, it would be, you know, near perfect, right? So the capacitors, output capacitors, have to hold up the output in between these, these couple micro. Well, let's see this off time. So let's see what that is. Okay, the off time is about 1.28 microseconds. So it's only just over a microsecond off, and it's probably about same here, same here. So even though our duty cycle is only 30% and our frequency's 147K, we're only off a little bit in between. So that's the beauty of mixing two phases together. So you get a yellow pulse in between two blue ones, or or a blue one in between two yellows for that matter. But it kind of fills in, so the output capacitors don't have to work as hard. For that matter, the input capacitors. So let's look at the input and output voltage ripple. Alright, so I switched the probes over. I'm looking at the DC output and the DC input. So I replaced one of those scope probes with a differential on channel 2. So on channel 2 it's 10 volts per division. And channel 2 is on the output, so it's 10, 20, 30, 40, 8 volts. And channel 4 is 5 volts per division. It's the other differential probe. And, let's see, I can line this up on a same division. Pretty close. 5, 10, 15, just over 15 volts. 15.7 is what I have on the Kaiweets. And looking down here, 15.9. So, pretty close. There's our input and output voltage at DC level. I'll turn on the load, and you see the input drop down a little bit, 15.4, but it's kind of hard to see what's going on, right? So we got to AC couple them. Okay. So we'll AC couple, then that way, here, let's center them in the screen. And then, let's see, I'll just grab this one. On channel 4, I just hit the button over there, just pushed in and it centered it for me. So, there we go. Okay, now, let's get a few more cycles. So, a few more. Okay, now let's just zoom in a little bit closer. So, let's look at 100 millivolts per division, maybe. Now it's going to be a little bit noisy, so we'll probably do a bandwidth limit. Here, let's just see what happens. Let's turn on the load. Alright, here we go. So I'm going to bring up the voltage. This is the input voltage, and this is the output. The input's 50 millivolts per division, AC coupled. 50 millivolts, AC coupled here too. I thought I had that different, but okay, 50 millivolts. Let's go ahead and bring it up, see if we have to change that. Okay, there's 17 volts at the input, and you can see the input ripple, and the output looks pretty darn good, right? Now that's no load, so let's go ahead and turn on the load. 2.5 amps, there we go, and the output ripple still looks really good. 50 millivolts per division on a 48 volt output, so that's pretty darn good. About 130 watts, but look at the input. We have this low frequency ripple, right? Now, check this out. If I zoom in, it looks pretty good. But here, let me freeze it. But it looks like some low frequency stuff going on. This is 500 nanoseconds. Let's do 2 microseconds so you can see the switching of the FETs. But yeah, the input looks a little bit strange, right? Because we have this low frequency ripple, which looks like that. Now let's see, if I try to get the cursors somewhat lined up there. Okay, they're almost there now. Here, let me get the blue one out of the way. Okay, it's about 2 kilohertz. Here, I'll put this guy in the middle. And I'm going to go ahead and put the green one in the middle too. I just kind of separated them so we could see them, but now we can see them relative to each other and see a better picture. Okay, now watch this. I'm going to go ahead and run it again. Our load's still going. So now let me bring up the voltage. Look at that. 18 volts, 19 volts, 20 volts. It's almost gone. There's 22 volts. Here, let me freeze that. Turn off the active load, turn off the power supply so we can see if the fans will turn off. Okay, again, the output looks really great, 50 millivolts per, but look at this. Now, as far as 50 millivolts, so the actual ripple looks pretty good, but you know, you can see kind of some spikes. Now, if we zoom in, that's our switching frequency, these little notches right here. I'll show you that in just a moment, prove that. But yeah, but you can still see a little bit of a low frequency ripple. But now it's a little bit higher frequency, right? It's a little bit higher frequency, but low frequency relative to the switching speed. Okay guys, here's the thing running right now. No load, okay? Now watch when I turn on load, you're going to hear something too. Okay, now that's 15 volts where it was before. Now I turn on load, look at that, nothing. And that buzzing is coming from my big HP power supply, my big linear power supply, and it's drawing about 7 amps at the input. Now, isn't that interesting? Now, if I drop the voltage down, if I go up, it doesn't really change. Okay, we're going to talk about this stuff here in a little bit, okay? Alright, here we are again. Power supply is running, no load. Let me turn on the load. There we go, 2.5 amps. And we're only at 16 volts input. Now I'm down at close to 15. We're not seeing that ripple, right? Now I'm going back up to 17, 18, 19, 20, so you can just see how it's going to move a little bit as I move it because it's AC coupled and it has to settle in. Okay. And there's 24 volts. Alright, I'm going to turn off the load. Alright guys, I'm running at 15 volts on the Kaiweets, and let's go ahead and apply the load. And we got the sine wave back. Now watch, I'm going to drop the load. I'm down at 2.2, 2.1. There we go, about 1.5. And sine wave's gone. This can be an interesting topic that I've been wanting to bring up, so I just want to show you because this is going to be kind of cool. We're running again, this time on the iTech power supply. And there we go. That's 1.5 amps. Everything looks nice and solid. We're at 15 volts input. Okay, I'm bringing up the load. I'm 1.9, 2, and look, 2.1, it goes crazy. So let me take up the voltage a little bit, 17 volts. And, okay, we're at 2 amps, 2.1, 2, 3, and then it goes crazy again. Alright. This is going to be a great discussion in the next video. Alright guys, I want to show you something else. I'm going to go ahead and apply 17 volts on, okay? There's 17 volts. Now the green one's the input. Look at that. It takes a dip, then it rings, and then what the heck? And the output kind of jumps up, and it's 50 millivolts per, so it's 100, 150, 200. Now here's the reference right here in the middle, so it looks like an AC waveform, right? Because it's in between this. So there's a step there. So let's collect some more time here. There we go. Look at that. So now we're at 20 milliseconds per division. We got 1, 2, 3, 4, 5, about 100 milliseconds. And this ripple is, you know, about 150 millivolts up and about 50 millivolts down. You know, something like that. But yeah, so this is what we call burst mode. Okay, so with no load, it just kind of, instead of just sitting there with really small duty cycle, it kind of does a little burst, charges up, and then discharges, then charges up, and then discharges. So let's go ahead and add a 0.1 amp load. Look at that. It corrects it right there. Zoom in. Well, not quite. It's still kind of in a burst mode. Just a little bit higher frequency. Let's go to 0.2. You see how it's getting a little faster and faster? Okay, there's 1 amp. And that's kind of strange looking, right? And then it just keeps on changing until we get to 2 amps, and then it goes back to what looks kind of normal, right? That's what you call burst mode, okay? Alright, here we are again. Let me apply 17 volts. That looks pretty good. There's no load. Wow. Looks way better, right? I'm at 10 microseconds per division. I can get some more waveforms, or more time. There's 100 milliseconds. I don't see any bursting going on or anything. Wow. So, looks better, right? And that's no load. Now, I'll go ahead and apply a load, 0.1 amp. Really no change. Now, here's the thing. If I go ahead and look at the pulsing, okay, I need to zoom in on that. Look at that. Here, let me freeze it. Looks pretty weird, right? This is pulse skipping. So it pulses, it skips, and then it pulses. 1 microsecond per division. So now we're going 1, 2, 3, 4. You know, you can see. Now that's 0.1 amp load. Let me run it again. And I'll... Nope, that's 0 load. Now it's 0.1. Still pulse skipping. Okay, 0.2, 0.3. There's 0.7. You can see here, let me freeze it. There's less skipping. See, it's starting to fill in. Okay, 9. There's 1 amp, 1.1, 1.4. Okay, well, 1.9 finally cleared up. So there we go. So that's pulse skipping. Okay guys, I'm powered back up again, running 0 load. There's no load on it, and we're not pulse skipping anymore. And if I zoom way out, there's no low frequency ripple either. There we go, low frequency reject. Okay, see, it's regulating, so the pulses are kind of changing, and so that's why the trigger was jumping around with high frequency. This is low frequency, but you can see the pulses kind of vibrating, getting wider. And there's a 1.9 amp load, so you can see the ripple up here. Yeah. So no load, load. And if you notice, the blue ripple hardly even changed. Okay, no load, 1.9. I'll go to 2.5. And then we start going into that weird stuff. Alright, so let's take a look at the spectrum. Okay, the output's channel 2, right? Now, if we spread it out, we can see we got a 2.5. Let's see, we have a 2.5 amp load. If I adjust the trigger, you can see the pulses. Okay, so let's go ahead and look at the spectrum. Okay, so we're gonna need to get some more pulses in here, and turn on the FFT. Okay, and let's see what the bandwidth is on that thing. We got 20 dBs per decade. We got dBs. It's channel. Channel 2, what we want to see. Okay, and Blackman, that's good. Okay, I think that's good for now. And here's the FFT. Alright, but if I look at the cursors here, like if I take a look at this cursor, I am at, let's put on the FFT, I'm at 6.5 megs. So what if we zoom in, get a little tighter? Well, first of all, I have to roll this over this way. If I put in the center, then I can spread it out. Okay, I need to get more cycles, I think. Okay, let's see what we have here. Okay, let's get this guy on that peak right there. Okay, that is 147 kilohertz. And that is almost 300 kilohertz. So yeah, and then we have some harmonics from that. Just here, let me freeze this. All right, so here, let's get rid of the blue channel 2 so we can see it a little bit more clear. So right here is a reference, and it's 20 dB per, so it's 20, 40, and this one's just below 40, and this one is almost 60 dB down. So if this is 0 volts, that'd be 100 millivolts and 10 millivolts, and so we're somewhere between 1 millivolt and 10 millivolts. Alright guys, so what do you think? Pretty cool, right? These polyphase converters are pretty neat. Running smaller parallel circuits versus big, single circuits to to handle all the current. I think it makes it more robust and more reliable, and also you don't have to switch to FETs as fast, so you get less switching losses. So there's a lot of advantage of having these kind of circuits. Pretty cool control chip. Doesn't take a lot. You can see the capacitors are really small, and yeah, some really cool advantages. Now, one thing you might be asking, like, hey, what about that weird thing when you showed all these different power supplies? I showed the Xantex, the Kaiweets, the iTech power supply, and this big old linear back here. You could hear that kicking on. And I use this electronic load, right? But that is, I'm just going to tell you so I'll just kind of tell you in a simple manner right now, but I've got another video that I'm going to do, which this was kind of cool that it came up, because I was actually going to do the other video first, but then I thought I'd do this just to show you the board. But the video I wanted to talk about is a really important video, and it has to do with impedance matching and impedance of power supplies versus the impedance of your load. And you can see how, depending on the power supply you used, it kind of caused some issues. They ran okay, but at the lower voltages, where it had to take a lot of current from these power supplies are rated for that power, but you saw some interesting sine waves, where it kind of has a ripple at the input, right? So next video, we're going to talk about that. Alright, so I want to give 2 thumbs up, as always, to my patrons. I really appreciate you guys. You become a patron for as little as $1 a month. And what else? Oh, we got t-shirts, not these shirts. Some shirts my wife designed. Hats. You know what else I got to show you? I keep forgetting about these. We got these little, notebooks you can keep at your bench. And pretty cool. Anyway. So, yeah, you can buy this kind of stuff too. That's an easy way to support the channel. Fairly cheap. A free way to support it is just to like the video. That helps a lot with the YouTube analytics and all that kind of stuff. So, appreciate it. And next video is going to be really cool. A really important concept in switching power supplies. And other things too. But, yeah. What do you think? Pretty cool eval card, right? Alright. Hey, thanks for watching. See you next time.